sordu. Arkadaşlar açın şu kameralarınızı.
Ben sordum hocam. Hayır.
Adını söyler misin?
Hayır.
Hayır, çünkü burada soruyu göremiyorum sizi. Şimdi peki. İstersen ders notlarına geri dönelim. Mesela şunu soruyor olabilirsin, değil mi?
Evet evet. Bunlardan ben sordum.
Bak burada tek bir çizgiyle parçayı ikiye bölebiliyorsun. Oldu mu?
Evet.
This is not a closed box. So with a single line here, it is possible for you to separate a portion away. Is this clear? Değil mi?
Evet.
Yani bak şu tek bir kırmızı çizgi, yani tek bir alanla parçayı ikiye ayırabiliyor musun? Ayırıyorsun, değil mi?
Evet yetiyor. Evet.
Tamam. Şimdi belki şurada başka problemlerimiz de vardır. Örneğin buna bakalım. Şurada tek bir çizgiyle, yatay çizgiyle ikiye ayırabiliyor musun?
Evet.
Ayırıyorsun. Gene bir sorun yok. Velhasıl, for example, this one, you can easily remove the part below, for example, below A with a single line. Bak burada şunu yapabilirim esasında. Gerek yok ama. You may just use another line here. You may use both of these two. But this time Q will be twice and T will be twice. Is this clear? No need. But anyway, the key answer is this. With a single transverse, with a single longitudinal plane, which is a line here, you can divide the body into two. Oldu mu?
Evet hocam. Tamam.
Yani tabii bu bir uzunlamasına bir düzlem. Mesela hep düzlemden bahsediyoruz ama hep cross section'da bir çizgi olduğu için ben çizgi diyorum. Bir çizgiyle bölüyorsun. Şimdi gelelim bizim son çözdüğümüz sorulara. Şuydu galiba. Now look. Is it possible for you to divide this? For example, I am looking for the shear flow on this line. So can I remove a portion away with a single line from here?
Yok.
Yok, değil mi? O zaman ne yapacağım? Eğer buradan da
Evet.
kesersem, hani bu kesme lafları falan tabii hayali düzlemler ama unutmayın. İnfinitesimal ayrımını böyle yaptık. Artık şurayı ayırabiliyorum. Oldu mu?
Tamam hocam. Teşekkürler.
Alırken nereye alacağım? Tabii ki simetrisini alacağım. Çünkü burada Q ile burada Q aynı. Örneğin şunu alsaydım, istersen bir önceki probleme geri dönelim. Mesela şu soruda bunu alsaydım, if I had taken this, okay. Yine mi takıldı bu? If I had taken this and this, for example. Now, this would be wrong. Why? Because the Q here is not equal to Q here. Okay? But if I have taken this one, these Q's are the same. Therefore, I end up with a correct answer. Right? But still, in these problems, one cross-section is not enough to write the force balance. Oldu mu?
Oldu hocam. Sağ olun. Teşekkürler.
Bu da nereden geliyor? Tekrar geri dönersek. Aklınızda eksik kalmasın diye tekrar geri döneceğim. Bakın, şu derivasyonda, in this derivation, bir önceki hafta mı? 16.5'te değil. O zaman şurada yaptık. Okay. Now look. Look at this figure. Here we removed the section. Okay, but this section is something like this, in fact, although that's the unit area. Now, the moment on both sides are in equivalence with the shear force. So to talk about the shear force, I had to remove a portion. Look at this green plane here. I am dividing into two because I am looking for the shear force on that plane. For this purpose, I should separate into imaginary parts to transmit force from one portion to the other. In I-beams, I can do it easily, but in closed boxes, to determine that plane, I have to use two symmetric planes. Is this clear? Oldu mu? Sor. Aha. Simetrik değilse zaten bu bizim bu chapter'ın konusu olmuyor. Yani vertical vertical eksene göre simetrik değilse o ansimetrikleri anlatmadı. Kitapta var esasında. Bakarsan görürsün ama biz sadece simetrikleri konuştuk. Tamam. Yani nötr eksenden kitapta o chapter onu bu derste anlatmıyoruz. Simetrik olmasında şunu yapıyorsun. Yap benim ona da. Principal central eksenleri kullanıyorsun bu sefer aynı mantıkla. Okay. Is this clear? So first find the principal central extent, refer this equation to those. But it is not a part of our derivation. Okay. If you don't have any questions, now I am starting a new chapter. Now, I am going to start this chapter first without writing because I wrote these yesterday to be fast. Why? Because the initial portion of this chapter, which I'm just going to show you through these, let me say, OneNote presentations, are depending on statics and trigonometry. So there is nothing with strength here, except the stresses, but you know them well. So I'm going to follow this first, and then in the Moore circle, I'm going to start writing again to be fast and save from time. Now look, this is the new chapter. This is chapter 7 in the book, as far as I remember. Ben chapter'ları böldüğüm için chapter yazıyorum sadece. Kitaptan bakın. Now, I'm talking about the transformations of stress and strain. Look, transformations of stress and strain. Now, at this point, now let us remember the equations that we learned. We learned that normal stress, şöyle bir özet yapalım. Sigma is equal to F over A, axial loading. Okay, tau is equal to T over J, torsion. Sigma is equal to MC over I, moment. Tau is equal to VQ over IT, shear. Okay, normal force, torsion, moment, shear. We learned these, and you have to know these equations very well. But look, all these equations are for cylinder members and with a section perpendicular to the axis. Don't forget, all these equations, bending, torsion, whatever, are for such cylinder members, and we refer to a plane perpendicular to the axis of the member. Is this clear? Doğru mu? Now, say that you have an inclined welded area here, a weld which is inclined. You cannot use these equations for this inclined plane. They are not valid for that. They are valid for this plane which is perpendicular to the axis of this member. What you will do is this: calculate everything with respect to this and then transform to this plane. Okay, that's why we are using these equations. So first, we use our equations for the plane that we have already discussed, and then transform these stresses to the plane that we are referring or we are looking for. So that's the purpose of this chapter. But we will not do for a three-dimensional case. Instead, for two-dimensional case, you can easily extend later in the advanced courses to three dimension as a result, even with the tensor analysis. Now look, okay, consider the stress state shown below and infinitesimal cubic element at Q within a meshing element. So we have a meshing element, and at point Q within the element, at a part Q, at Q we have this cubical element. Is this clear? Now, there is a stress tensor on it, and you all know the stress tensor from the first chapter. Okay, say that you know everything about the stress chapter. You know all this. Excuse me. Arkadaşlar bir saniye, bir şey oldu burada. Tamam, düzelttim galiba. Görüyorsunuz değil mi? Ne oldu ben de anlamadım. Her neyse. Now, assume that you know all these stresses. You have calculated them from torsion, from moment, from axial loading, from shear force, whatever. You know all. With respect to X, Y, Z axis. But at the same point, if you rotate the element to a new orientation, still you have a stress tensor, sigma Y prime, tau X prime, Y prime, but their values now change. Look, you have the same loading, you are at the same point, only the orientation of the coordinates are changing. Now, your stress state is also changing. Your components of the stress tensor is also changing. Is this clear? Okay. So it is coordinate dependent problem. Now, let us start with the plane stress. So we will be discussing this for a plane stress problem. What is plane stress? Plane stress is a stress state, The stress is in one direction. Generally, we prefer Z, but doesn't matter. You can use X and Y is zero. We discussed this previously before. So, what's a plane stress problem? For example, this is a plane stress problem. Plane stress problem is not, of course, the exact case, but an approximation to the solution. This is a plane stress problem. Whereas if you have a thin member like this, and if all the forces are in plane and acting on the mid-surface, it is a plane, it could be regarded as a plane stress problem, just like this paper. You have a thin plate, thin member, its thickness is small, and all the forces are within the plane. You never have a transverse load like that. Okay, then this is a plane stress case. İnce olacak ve bütün kuvvetler yüzeyin içinde olacak. Tamam? Or, this is also a plane stress problem. A cubical element on the surface. Why? Since it is on the surface, and since there is no loading on the surface, you can assume it as a plane stress problem, although the body is not thin and a three-dimensional body. Because always on the surface of a member, if there is no loading, basınç olmayacak, başka bir şey olmayacak, if there is no loading, then it could be assumed as a plane stress problem. As a result, in a plane stress problem, the cubical element is this, assuming all the stress in Z direction zero. So, in a plane stress problem, the basic assumption is this. The stress is in one direction, say Z, are all arkadaşlar, gene bu kalem yazmıyor. İzninizle şunu bir kapatayım bir daha için. Anlamıyorum ne oluyor yani buna. OneNote'daki bir problem var. Nedir? Anlayamadım bir türlü. Niye böyle oluyor onu da anlayamadım. OneNote. Neyse yani devam edeceğim çünkü zaten orada ekranda yazılı. Bir kez daha deneyim bakayım niye böyle oldu. Neyse. Devam ediyorum çünkü zaten ekranda var. Now look. Görseli görüyor musunuz arkadaşlar en azından? Görseli görüyor musunuz?
Evet hocam.
Tamam. This is the basic assumption. Gidebildiğimiz yere kadar gidelim. Olmazsa başka bir tablet deneyim. Here, this is the basic assumption. In Z direction, normal stress is zero and all shear stress are zero. On the other hand side, in the plane, sigma x, sigma y, and tau xy are non-zero. Of course, one of them could be zero because of the loading type, but in general, these three stresses are non-zero. As a result of this, look at the strains. This time, Since sigma x, sigma y are non-zero, epsilon y and epsilon x are non-zero. Since tau xy is non-zero, corresponding shearing strain is non-zero. However, epsilon z also is non-zero. Why? Who is going to tell me? Neden?
Poisson's ratio.
Because of the Poisson's ratio. Although we do not generally consider that, it is zero, right? Anlayamadım gitti arkadaşlar. Yani bu durduk iş yapmıyordu bugüne kadar. Bir tableti ayrım takayım bakayım bir kez daha. Belki bundandır. Heh. Yani arkadaşlar ne kadar lüzumsuz işlerle uğraşıyoruz ya. Bu memleketi anlamam benim mümkün değil yani. Hakikaten anlamıyorum hiçbir şey. Ne insanından ne yalanlarından. Şimdi bakın arkadaşlar tekrar altını çizeyim. This is the plane stress assumption, right? And although all these stresses in the transverse direction or in the z direction are zero, because of Poisson's ratio, this is non-zero. But still, keep in mind that we do not use this in the constant equation. I mean, in the stress-strain relations. Maybe it is a little bit advanced knowledge, but anyway. Now look, let's talk about transformation of the stresses. Look on the left, look at this element, right? Look at this element. On this element, we have a stress state. And say that you know sigma x, sigma y, tau xy, you know all. Then we are rotating this element as much as theta. Okay. Now we don't know the new stress state. At the same point, we are not somewhere else. At the same point in the meshing element, if you have a gear, at the same point, right? Then we are just using an infinitesimal element. So look, we are taking a portion from here where this is parallel to this face. So now we have this element. On this element, this is delta A. And since this is delta A, you can easily talk about these areas just from geometry. This is clear. Now, okay, what we have is this. This time, I am drawing the element once more here. Now we have such an element, okay, and the coordinate system is clear. We have x and y and z, and we have new coordinates which are x prime and y prime. Sorry. Yanında zaten güzel şekiller var. Y prime. Now look. Farz edin ki bunların hepsi aynı yere geldi. Gelmemekle birlikte. Biraz düzelteyim şunu da. Now, what is the new stress state here? The new stress state is this. I have a normal stress in this direction. Okay. I have a normal stress, sigma x prime. And I have a shear stress here, tau x prime, y prime. However, on the other hand side, look at the cube above. On this cube, we have already sigma x from here. We have already sigma y. And we have already these shearing stresses tau xy. They are already on the cube. Oldu mu arkadaşlar? Bakın şunları sileyim tekrar göstereyim. Şimdi on the surfaces which are parallel to this cubical element, okay, we have sigma x, tau xy, sigma y. On the surfaces which are parallel to this cube, we have sigma x prime and tau x prime y prime. Oldu mu? Yani şunlar. Now, then we now multiplying these stresses with the corresponding areas. Now, when we do it, we obtain the forces. Oldu mu arkadaşlar? We have stresses shown above with those cubical elements. When we multiply those stresses with the areas shown on this figure, now we have forces on the cubical element or on the infinitesimal element. We multiply stress with the corresponding area. We have forces. because stress is per unit area. We multiply it with the area, we have forces. The next thing is this. Just write the force balance in x direction and y direction. For example, sigma x prime delta A. Sigma x times delta A is the force. This is the component of the force in x direction, etc. From statics, you can write these two. So, once you have written these forces, once you eliminate the higher order terms, once you use trigonometric relations, you end up with these three equations. These three equations relate the old stress state, the first coordinate stress state which you know, to the new stress state, prime stress state. These equations are somehow similar to the moment of inertia equations that we use for inclined sections. So with equation 1, 2, and 3, by knowing angle theta, we can determine the stress state on the new cubical element which has been rotated by angle theta. Oldu mu arkadaşlar? Yani tek yaptığımız statikteki kuvvet balance, yani kuvvet sum of the force equals zero'yu kullanarak stresleri birbirine eşitledik ve açılar cinsinden birini diğerine göre yazdık. Buraya kadar bir sorunuz var mı? Peki. When you look at these three equations, you see that as you rotate this angle by theta, okay, as you rotate this angle by theta, sigma x prime, sigma y prime, tau x y prime are changing. From 0 to 360 degree, for each angle, of course, there are infinitely many angles. If you consider all possible small increments, there is a new stress state, sigma x prime, sigma y prime, sigma z prime. So if you know your angle theta, find the stress state. But now the question is this, for this part of the problem. What is the angle where we have maximum stress and maximum shearing stress? Is this clear? Now look, according to the procedure given in our book, which I don't like, but I'm going to explain, the first and third equations, these two, remember your math courses, are the parametric equations of a circle. These two are the parametric equations of a circle. So therefore, if you eliminate theta from these two, what do you obtain? Look at the book. I mean, it's very easy to eliminate theta from these two. Just math. And you get such an equation. Or you can write this equation in this form. This equation is an equation of a circle where instead of x, you have x prime, x sigma x prime. Instead of y, you have tau x prime y prime. So therefore, you can draw the circle not on xy, but sigma x tau plane. So what you have is the circle. Is this clear? So from the transformation equations 1 and 3, you end up with by eliminating theta, an equation similar to a circle in xy plane, but now this time the planes are normal stress and shearing stress, and this is our circle. Now look at this circle carefully. Okay. Now on this circle, this point is the point where you have, siz söyleyin lütfen şimdi, burada ne var arkadaşlar? En büyük, what is this?
Normal stress.
Normal stress. This is the smallest normal stress, because in plane stress, all your possible stress stays on the circle. Okay. So then this is sigma max, this is sigma min, this is sigma average. What about the shearing stress? The shearing stress is maximum at D and E. So this graphical illustration shows us, I'm going to later how to draw this in detail. Sadece şu anda görün istiyorum. How to determine the maximum stress, minimum stress, and maximum shear by using graphical approach. How? We will discuss it. Anyway, now look. Okay, then how can I locate sigma max or sigma min with respect to my current stress state? What you are going to do is this. Okay, just take the derivative of this, for example, with respect to theta, alamadım yine. Take this with derivative with respect to tan equals 0. So you can find the XMU values. And when you do that, we have this equation. And this equation says that at this angle theta, you have the principal stresses with respect to your current location. Oldu mu arkadaşlar? On this Moore circle. Yani şunu demek istiyorum. Say that your current stress state is here. So the angle between maximum stress and this is 2 theta p. 2 times theta p. Just from geometry. Or look at the circle. This circle says that sigma max is equal to sigma average plus radius of this circle. Bana söyler misiniz? Radius of this circle aynı zamanda shear stress cinsinden neyi söylüyor size? Radius şuradayken neyi veriyor size arkadaşlar? Maksimum
Shear stress.
stresi veriyor değil mi aynı zamanda? Peki. Dolayısıyla when you use this theta p in these equations, now you obtain maximum and minimum shearing, normal stresses. In the same manner, by, as a result, the maximum and minimum shearing stresses are obtained with this equation. Average, şurada artıyı unutmuşum, plus or minus sigma x plus sigma y over 2 plus tau xy square. Plus means minus, minus means minimum. Okay. And once you obtain equation 1, use equation 1, you can also say that at this angle, you have maximum and minimum shearing stresses with respect to your current stress state. And this is the equation of tau max, the maximum shearing stress, where you can obtain by use this average from here. Okay. So the maximum shearing stress occurs where you have the average shearing stress. Bundan sonrasını yazarak devam edeceğim. Tekrar geri dönüyorum arkadaşlar buraya. Ve bir kez daha özetleyeyim. By using such a cubical element, now this stress state is new. We rotated the element as much as theta and obtained this stress state. Then, from force balance on this infinitesimal element, we obtain the relations between stress and strain. So these three equations are important because these equations gives us the stress state for plane stress at any angle theta, if you know, of course, the original stress state. And this sum is always an invariant. Then, since equations 1 and 3 are the parametric equations of a circle, we can show geometrically the stress state on such a circle. Again, now on the circle, you know A and B as the maximum and minimum stress, and D is the maximum shearing stress. Look, arkadaşlar buraya bakın. Whenever you have maximum shearing stress, tau max here, the corresponding normal stress is always sigma average, given with this equation. Demek ki bir yüzeyde tau max'iniz varsa orada normal stress sigma average. Bunu bilmeniz yeterli. Bir şey daha var. Whenever you have sigma max or sigma min or maximum or minimum stress, what is the corresponding shear stress on that plane? Yes? Ne diyor bu?
Zero.
Zero. Okay. So, therefore, the stresses at point Q defined by A and B are called as principal stresses. O halde principal stress deyince aklınıza ne gelecek? Bu yüzeydeki en büyük veya en küçük normal stres. So when we say principal stresses, you should understand that you are talking about either maximum or minimum normal stress on a plane. That plane or those two planes which are perpendicular to each other are called as principal planes. And what we know from this figure is that on the principal planes, the shearing stress is zero. Whenever you have maximum normal stress, maximum shearing stress, the normal stress on the surface is average, sigma average. By the way, the last thing maybe I can say here is this, before drawing the Mohr circle, which make this further clear. The angle between the planes where you have maximum normal stress and maximum shear stress is here 90 degrees. Oldu mu arkadaşlar? Bakın D ile A arasında 90 derece var. But this is 2P. So the actual stresses are making 45 degree with each other. Okay, on the cubical element. Buraya kadar bir sorunuz var mı? Peki.
Hocam son cümlenizi tekrar eder misiniz?
The angle between point D and point A, one is sigma max, the other one is tau max, is 90 degree on this circle. But this circle uses angle 2 theta P. So on the actual cubical element, this angle corresponds to 45 degrees. Okay. Şimdi Mohr circle'da bunları tek tek yazarak anlatacağım. Çok daha iyi anlayacaksınız bu girişten sonra. Orayı yalnız iyi takip edin. Çok basit esasında ama yani burada statikten gelen bir force balance'dan bahsediyorum. Şimdi Mohr circle'ın steplerini yazacağım. Vaktim kalırsa bir de onunla ilgili örnek çözeceğim. Burayı yazmak istiyorum. Okay. Now, this circle is the Mohr circle. This is the Mohr circle, which is first obtained by a German called Mohr. And I am going to now tell the steps how you can obtain this Mohr circle. Bunu kitapta benim yazdığım gibi bulamazsınız. O yüzden benim bildiğim gibi yazın lütfen. Önce bunu uzun uzun yazayım. Sonra şey yaparız. Mohr circle'ı çizeriz. Bakın. Deminki soru, I am talking about the previous circle. How can you draw it? Okay. They are parametric equations. You can draw the whole circle. I'm not talking about that. I'm talking about this. You know your stress state. Knowing that, how can you determine the Mohr circle? Now, Mohr circle, bunu çizdiğim zaman bütün bu söylediklerim daha iyi anlaşılacak. Mohr circle for plane stress. For plane stress. Now, this is a procedure. But anyway, I mean, okay, let me say and then tell later. The circle, which is used to determine, the stress vector, on an arbitrary element, okay, in terms of, or stress tensor maybe, isterseniz stress tensor diyeyim şuraya ya da stress component diyeyim, daha iyi olacak. Sonra anlatırım şeyin detayını. Components on an arbitrary element in terms of sigma x, which you know, sigma y, which you know, and tau xy, which you know, is known as Morse circle for plane stress. Okay. Now, the stresses at any inclined surface may be found graphically as follows. Graphically as follows. Now look, arkadaşlar bu stepleri lütfen iyi takip edin. Yani ne kadar göstereceksem de. First, plot x, which is sigma x minus tau xy. Bakın, nerede? Sigma tau plane'imiz var. Xy değil yani. Tekrar yukarı çıkayım. Düzlemimiz sigma tau. Prime veya değil fark etmez. Okay. So first plot x. X means the cubical element surface whose normal is in x direction. Niye eksi derseniz bir prosedür. Artı olanı da var başka kitaplarda. Bizimki de eksi. Onu da sonra söylerim. Plot y. Y interprets the surface whose normal is in y direction. Sigma y, which you know, but this time plus tau xy. So you have 2 points on it. Okay. Then the third step is this. Now look, their taus are the same in magnitude. So center of this, okay, let me write first this. Join x and y, yani x'i buraya koydunuz, y'yi de buraya koydunuz. Bir straight line'e birleştiriyorsunuz böyle. Tamam mı? Göstereceğim. Join x and y by a straight line, okay, and define the center of the circle which we will be drawing by sigma average 0. İster istemez böyle oluyor arkadaşlar. Tavlar aynı olduğu için şey 0 oluyor. Göreceksiniz şekilde zaten. Bir saniye. Okay. Straight line. Now C is the center of the circle. Okay. C is the center of the circle. Yazayım isterseniz. Center of the circle. Then after this you have everything. Determine now sigma max, sigma min and tau max. Artık arkadaşlar hepsini biliyorsunuz. Tau max. Now, if you want, determine the stresses. Bu çok kolay bir yöntem esasında. Stresses for any plane with normal making an angle theta with x direction. I'm going to show it on the circle also. By laying off, this time, an angle on the circle. All the angles on the circle is 2 theta in the same direction. Okay, this is the procedure. Now, note that. Şimdi yönlere gelelim. Note that. One, the shearing stress exerted on a given plane to determine its direction. Exerted on a given plane. Okay. Or given face diyelim, daha kolay olacak. Çünkü kübik elemandan bahsediyoruz. On a given face, A rotates the element clockwise if the corresponding point on the Morse circle is above sigma axis. I am saying this, if this is sigma and if this is tau, we are talking about this region, right? Okay. And B rotates the element counterclockwise, the cubical element counterclockwise if the corresponding point this time, if the corresponding point on the Morse circle below the sigma axis. Okay. Bir de kitapta yazmayan bir pratik bir şey daha söyleyeyim size. Maximum shearing stress is always towards the largest principal stress. Okay. Şimdi 4 dakika var ama en azından benim şöyle rastgele kullandığım bir örnek var, kitaptan olmayan. Onunla başlayalım. En azından bir circle çizeyim, durayım. Consider, bu söylediklerimi anlamanız için. Consider the following element. Arkadaşlar bakın. You solve the problem. Then you have taken your cubical element. Then you attach a coordinate system to your cubical element. Bunları yaptınız hepsi. Bu şu ana kadar öğrendikleriniz hep bunları yapıyorsunuz. You have an element. And on this element, you know that you have sigma x, which you have already calculated, maybe because of bending. Sigma y, say compressive, maybe because of an axial loading. And shearing stress, maybe because of torsion. We don't know. I mean, say that these exist on the system, right? You have calculated this by using all the equations that you learned. Let's say that at the end of your analysis, sigma is equal to 100 megapascals, sigma y is equal to minus 25 megapascals, and tau xy is equal to 90 megapascals. So you know these from your calculations. VQ over IT, TC over G, whatever. Okay. J, whatever. Now, by knowing these, let's draw the Morse circle. Here I am saying that we always have three principal stresses. So, principal stresses in three dimensions are shown by sigma 1, sigma 2 and sigma 3. Bakın arkadaşlar, Mohr circle'ı 2 dakika içinde çizeceğim ve bırakacağım. This is, now to draw the Mohr circle we need two axes. One is the vertical axis, the other one is the horizontal axis. Horizontal axis is the normal stress axis, vertical axis is the shear stress axis. What is the first step? First step is plot x. What is x? Sigma x minus tau xy. So, look at the values that we know. So, sigma x is somewhere here. Tamam mı arkadaşlar? Sigma x minus tau xy. Yani 100 artı 90. Pardon, eksi 90. Oldu mu arkadaşlar? Takip ediyor musunuz bilmiyorum. Şunu çizeyim duralım. Yarım kalmasın. Then what is y? Y is minus 25 plus 90. So y is somewhere here, right? Y is somewhere here. Okay. This is point y. Use sigma y and positive tau xy. Then join these two with each other. Intersection is the center of the circle. Then just draw the Mohr circle. Say that this is a perfect circle. Then, okay, let me draw the circle once more. This is the Mohr circle. Now look, very easy. This is sigma max. This is sigma min, right? This point is tau max, if you draw such a vertical line. And then this point is tau max, but minus. This point C is sigma average. And this angle is 2 theta p. Oldu mu arkadaşlar? Burada duralım. Gördüğünüz gibi bildiğiniz yerde kullanarak Mohr circle'ı rahatlıkla çizebiliyorsunuz. Bundan sonra elemanın rotasyonundan bahsedeceğim. Dolayısıyla stres testi biliyorsanız bu kadar basit Mohr circle'ı çizmek. Yukarıda söylediklerim hep bunun şeydi, açıklamasıydı. Peki. Sorunuz var mı?
Evet, Profesör, buradaki stres axial stres magnitude olarak en düşük şeyde değil mi? Tau'nun yani tam C'nin hemen solundaki aksisti.
En düşük, normal stresini sordu en düşük.
Evet.
Bu, şu.
Ama mutlak olarak
Hayır, mutlak bakmayacaksın. Büyüklük olarak.
anladım. Tamam.
Yani burada şöyle bir sıralama var. Mutlak bakmayın. Sigma 1 büyüktür sigma 2, o da büyüktür sigma 3. Tamam. Dolayısıyla
Tamam.
bizim bunu bu kitap çok kullanmıyor. Ben şöyle kullanayım burada. Bakın arkadaşlar, bir de şunu yazayım. This is the maximum shearing stress, sigma 1. This is the minimum stress, sigma 2, 3. Now, at this point, we have sigma 2, which is equal to 0. Because we always have three principal stresses, but in plane stress problems, one of them is always 0. Oldu mu? Peki, buradan tekrar Perşembe günü devam edeceğiz. Sorunuz yoksa kapatıyorum.